Okay, now we'll start discussing about joining in composites. As you can imagine, joining is very much necessary if you are looking at a bigger structure such as bridges, automotives, or aerospace structures. So let's say we are looking at manufacturing of an aeroplane. It cannot be prepared in one single piece. Of course, there are several thousands of components which needs to be assembled together. Now the question is, if we are designing a composite based structures, how do we assemble it, or which joining processes do we choose so that these can be assembled in a more efficient fashion? So when we discuss about joining, we might be either joining two composite substructures together, or it is also possible that one of the composite substructure you are adding it or joining it to a metallic component. So meaning we need to not just focus between joints between composites and composites, but also we should focus on joints between one composite and another metal. Then joining also helps us to come up with complex structures which cannot be designed or manufactured in a single component. So this gives you a design flexibility so as to come up with more efficient structures where a complex structure is the only way to solve the problem. And lastly, we are also saying joining is used in repair. So let's say when somebody notices, maintenance notices a damage, how do we fix those damages? So one of the solutions is to repair using joining methods. So now let's look at few of the examples of joining. We'll start with mechanical fasteners. So these are the very traditional methods we have used also in the metals. So like using riveted joints, bolted joints, and the pin joints. So the same can also be applied with composite joints. But in addition to that, there are other alternatives which in some instances are much better than mechanical fasteners. The more commonly used is the adhesive bonding, where let's say let's call these as substrates. So substrates are ones which are either made with metal or composite. So this could be a composite laminate or maybe a metal sheet. And in between, to join these substrates, let's say this is substrate 1 and this is substrate 2. To join this, we use a material called as adhesive. Adhesive is most often a polymer based material, and the very commonly used structural adhesive is epoxy. So this is a material which bonds both these substrates together and gives strength. So it resists either deformation or failure of this bond. So we'll discuss more about it later, but let's also see what are the other methods of joining. So we can also see the ultrasonic welding, where they use high frequency waves to melt the surface of the composite. So once you melt the surface, then you can join it because of the melt. And the other commonly used method is the friction stir welding. Again, we use the friction to help with the welding of two composite parts. And lastly, there is also called as hybrid joining, where instead of relying solely on one particular joining method, you mix two methods. So for example, here is a bolted adhesive joint where we have a bolt here as well as the adhesive here to achieve the joints. Because in some instances, though we know, let's say the adhesive bonds are really good for composite structures, sometimes it is better to go with a strategy which is more reliable to be fail safe. So in those instances, we go with this hybrid joining where, for example, here we are showing bolt and adhesive, but it could also be any of these like rivet plus adhesive or pin plus adhesive joints. Okay, now that we have seen what are the various methods, let's focus more into the mechanical fasteners and the adhesive joints. So we'll start with these mechanical joints. As already mentioned, when we talk about mechanical joints, we are either talking about bolted joints where this is the bolt and the riveted joints where this is the rivet, and then the pin joints where we have several pins. What are these pins doing? Essentially they are joining these two substrates, substrate 1 and substrate 2. Okay. So here we will be using not just one, but there will be several of these bolts and rivets or pins which will be used to join these two parts of the components. So what is common with all these mechanical joints is one needs to drill a hole so that this bolt can fit in, or the rivet or the pins can fit in. But when you start drilling a hole, it introduces a stress concentration. Because of this stress concentration, the failure most often initiates at the joint locations. And there is another disadvantage, meaning that it weakens the composite locally, meaning that you are removing some material from the composite, meaning the total strength is no more the same. The strength of the composite is compromised because you are removing a part of it. So let's also focus on what are the different failure modes one would expect in mechanical joints. Specifically, we will be focusing on the bolted joints. The reason why we are focusing on the failure modes is, as a designer, one needs to know how a design fails. Once he is aware of it, then during the design he ensures that those failure modes are at least taken care of. So here are three commonly seen failure modes. One is tensile failure. So as you can see here, let me change the color. So at the middle of the composite laminate, it fractured into two pieces. The way to avoid this is to ensure that we have more zero plies. So if we have more of these zero plies in this direction, then those plies will take the loads and we can avoid this, or avoid or minimize this tensile fracture. Secondly, for shear fracture, here you see that the failure is happening in the laminate in this location, and the reason why it is occurring there is because we are now shearing the laminate. And how can we improve these uh, shear resistance? By including more of these plus or minus 45 plies. We know that plus and minus 45 plies have the maximum shear strength. So if we have more of that, then the laminate is more resistant to these shear failures. And lastly, we are looking at bearing failures, where let's say initially the bolt is here, but then once we apply the loads, let's say if the laminate has a less resistance to bearing, then this hole gets elongated. How do we avoid this? This is simply by increasing the thickness of the laminate, because it indicates that we have designed it with insufficient thickness, and if you increase the thickness, one should be able to minimize this failure mode. And lastly, there are few other failure modes which are mostly out of plane. So let's say here there is substrate 1 and substrate 2, and we are joining with substrate 3 here, and then there is a tensile load on both ends. So then there are a few failure mechanisms which the bolt can fail. So here is a fracture of the bolt. As you can see here, since it is putting a lot of load on the bolt, this bolt can fail here. Or the bolt can also start lifting. So as you can see, this bolt is piercing into the laminate and damaging the laminate more. So this is also to be avoided. So in summary, these are the different mechanical joints people use in the composites, as well as the commonly occurred failure modes. We also try to show how we can minimize most of these commonly occurring failure modes. Now let's focus our attention to composite adhesive joints. As we already mentioned, here we use an adhesive which is mostly a polymer based material to join two substrates. So let's say this is substrate 1 and substrate 2. One of it is a composite, the other could be either a composite or a metal. So the reason why most often we use adhesive joints is because it creates a strong and lightweight joints. You might be wondering why it is lightweight, because here we are not adding any metals like bolts, rivets, or the pins which add weight to the structure. Instead, we are simply adding a polymeric layer which is of lightweight. And secondly, it does not compromise the integrity of the materials. So unlike mechanical joints where you need to drill a hole which compromises the integrity of the material locally, here there is no removal of the material or the drilling of the material which is required. So these are two primary features of adhesive joints which differentiate them with the mechanical joints. But now let's see what are the other advantages we get here. So we already mentioned these are lightweight. Why are these lightweight? Because we said we avoided using the extra metals like bolts, pins, or rivets. Instead, we are using this polymeric material which is lightweight, and it evenly distributes the stresses. So, unlike bolted joints where the loading is transferred from one substrate to the other substrate at these bolts, for example, here the loading is distributed over this complete area. So let's say the whole adhesive layer, this is the cross section, but the whole adhesive layer will take the load while it transfers the load from let's say the substrate 1 to the substrate 2. Meaning, why is it important? Because since the load is distributed over a large area, the stresses in the adhesives are much lesser compared to the stresses in the bolts or the rivets. And it also helps to dampen the vibrations, because we are using polymeric materials which are relatively soft compared to composites or metals. They can dampen some of the vibrations. And aesthetics too, we have a better advantage because now we will be getting a clear finish. So unlike bolts or rivets where you have some extra features coming out of the surface, here we can design adhesive joints such that these are very smooth and looks very pleasant to the eye. And these are compatible with various materials. This is very important, I would say, because unlike welding, so the problem, let's say, in welding of metals is some methods are only suitable for very specific joining of, let's say, aluminum is very difficult because it's not as straightforward as joining to steel bars. There we have differences with the melting, so we need to find a welding method which is much more suitable to, let's say, aluminum or any other material. But usually in adhesive joints, the adhesives we choose are compatible with most of the materials. Of course, it's not like for each and every material, but like 90-95% of the materials, these are compatible, meaning the same adhesives one can use to join aluminum, steel, as well as composite. So that's a greater advantage because one can use the same adhesives throughout the structure, let's say a car or an aerospace vehicle. So, but it does have few disadvantages which include longer assembly time, because this is a most often done manually, but of course now there are many automated procedures even for adhesive joints. So it does take more assembly time, not just because of the application of the adhesive, but it also take times to curing. I hope all of you remember what curing is, right? This is the process in which the polymerization happens and it goes from segregated polymer chains to connected polymer chains. So this curing usually takes like a long time if it is done at room temperature. So usually it takes like at most a day or more at room temperature. But to minimize the time, one can do it by curing it at slightly higher temperatures, because if you go at higher temperatures, this polymerization happens more quickly. So it can be reduced to as little as half an hour or even a little less than that. And these are very sensitive to surface preparation. So since we are joining two surfaces, the surfaces which we are joining needs to be prepared, in the sense like there are several surface preparation methods. One is you ensure that all the dust is removed, for which you can use alcohols like acetone to remove all the dust. But sometimes you also need to ensure that there is enough surface roughness. For that, either you can do sandblasting or use a sandpaper to scrape up the material on the surface. This ensures that the surface is rough enough and there is some mechanical bonds happening at the molecular level. And as we can assume, this is a permanent joint, meaning once joined, to remove it is not so easy. There are some instances where you can even remove after joining, but very rarely, and this has to be designed at the early stage of these structures. And since we are using polymers, these polymers cannot take high temperatures, so that's one of the weakness of these adhesive joints. So this should be put in mind before we choose any of the joining methods. Or here, if one chooses to go with the adhesive joints, these are few of the disadvantages and advantages one needs to be aware of. So now let's focus on what are the different configurations in which we can go with the adhesive joints, meaning what is the geometry of these joints. So there are several configurations. We look at commonly used configurations, starting with a lap shear joint. This is a very common way of joining two large plates. So once we have two large plates, you just need to overlap them, and this overlap region you apply this adhesive to join these two large plates, either composite or metal. And usually the loads are in this direction. So essentially this adhesive is resisting your deformation or failure through shear. So this is a lap shear, or we also call it as single lap shear, because there is only one adhesive layer. Now we'll look at a double lap shear. Here what is happening is we have two layers of adhesive, adhesive layer 1 and adhesive layer 2. And here we have two substrates to the left and one substrate to the right. The advantage of this double lap shear joint is, as you can see, since the bonding area is large, the stresses in these adhesives are small. This will help to avoid failures at this joint level. Or in other words, it can take now higher loads, because now we have a double shear or the double bonding area to take the loads. But one advantage of these lap joints is, as you can see, there is an offset. So if I extend this loading direction, and this is the loading direction on the bottom substrate, there is an offset in the load. Because of this offset, it can introduce some bending moments. Because of the bending moments, so the geometry of this structure will slightly bend about the joint, which needs to be avoided. So one way to avoid it is to use this single strap joint, because here the substrates 1 and 2 both are aligned in the same direction, so we can avoid those bending moments. So how did we do this? We add a strap and then apply the adhesive, so which transfers the load from one substrate to the other. Here too we can go with a double strap joint that will allow you to apply larger loads as well as to make the joint symmetric about this loading axis. And lastly, there are places where there are limited space. If there is limited space, one can go with this butt joint, meaning that you apply the adhesive just between these two substrates. But the problem is the area available to join is less, meaning the failure loads will be very less. So it will quickly fail. So one way to increase the joint strength here is to increase the joint area. How do we increase the joint area? By using a scarf joint. So as you can see here, now you have two objects. So this is, let's say, substrate 1, and then this is the substrate 2. So we are saying we'll use this area to apply the adhesive. So since we are now looking at an inclined line which is much longer compared to the thickness of these substrates, now it can take more loads compared to a butt joint. So these are the commonly used adhesive configurations, but Of course, depending on the application, there are many other configurations. One more application is a T joint. T joint is something like this. So you can apply the loads in the vertical direction, and once you add the adhesive in between these joints, so essentially one can able to apply the loads in the normal direction compared to these substrate, let's say S1. Lastly, we will also look at the common failure mechanisms we observe with adhesives. So the failure of these joint can happen in multiple fashions. We'll now focus on different failure mechanisms we see in these adhesive joints. To start with are the adhesive failure. What it means is it fails at the interface between the adhesive and substrate. And second is the cohesive failure, where we see that the failure is occurring within the adhesive layer. So ideally, people working in adhesives, their aim is to ensure that the failure does happen in this adhesive layer and not at the substrate. Like it doesn't damage the composite, but the failure does happen in the adhesive layer. But ensuring that these failure loads are much higher. So these are the commonly observed failure modes: the adhesive failure and the cohesive failure. But there are also other different failure mechanisms, which include the thin layer cohesive failure, meaning so the failure is in the adhesive like what we see here. It's a cohesive failure, meaning again within adhesive, but as you can see one of the layer is very thin, so it is very close to the substrate level. And the other is a fiber tear mechanism, because unlike metallic joints where the metals are much stronger compared to the adhesive joints, in the composite joints, the composite is the strength of the composite is comparable with the adhesive, meaning sometimes the failure can also happen in the composite. So here is one example where we are showing the failure is in the composite and it tears few of the fibers. And lastly, we are saying the failure occurred somewhere in the middle of the substrate, which we call it as the stroke break failure. So as you can see, there are several failure mechanisms, and these failure mechanisms are slightly different from metals, because in metals it is very rare to see like the fiber tear failure or the break failure, because usually the substrates are much thicker and stronger, and usually the failure doesn't occur there. But once we are discussing about the composites, it's possible that the crack grows into the composite and tears or breaks few fibers. Or it is also possible that the failure occurs at the middle of this laminate instead of the joint level. So now let's summarize what we have discussed in this video. We have looked at why we are interested in this joining, because as we know, once we are building up a big structure, it needs to be built as several subcomponents and they need to be assembled. And during this assembly, we use different joining methods like the mechanical joints, adhesive joints, hybrid joints, and few other joints which we discussed. In this video, we only focus more on the mechanical joints and the adhesive joints. For the mechanical joints, we showed the different options like the traditional rivet, bolt, and pins, and we also discussed about few failure mechanisms. There we were able to show how we can uh, improve the design of these joints to avoid common failures in bolted joints, for example. Later, when we discussed about the adhesive joint, we said it overcomes few of the disadvantages of mechanical joints, like It avoids the stress concentration at the holes as well as the compromising the material by drilling a hole. But it too has few disadvantages, like it has limitations of working at high temperatures and others. Later we focused on different configurations which people use to for the adhesive joints, like the single lap or the double lap or single or the double strap joints. And lastly, when space is limited, we said we can also go with the butt joint, but which are usually weak. But to improve the joint strength, one should go with the scarf joints. And finally, we also discussed the different failure mechanisms by which adhesive joints fail. Here, when we discuss about the composite adhesive joints, we said there are few mechanisms which are very specific to composites and which are not seen in a metallic joint, like cracks going into the composite where it goes and fails the fibers, as well as the failure occurring in the laminate itself, not away from the joint area. So with this, we will conclude this video. Thank you.